time for more reactions of aldehydes and ketones. Here's a reminder of our reactivity chart. Remember, aldehydes are more reactive than ketones, and both of those squiz right between anhydrides and esters on our reactivity chart. So we'll start off actually going backwards a little bit on the synthesis problem that you had to do. You were trying to synthesize 4-octanol from anything of your choice. 2 of the Grignard options we presented were Grignards attacking aldehydes, the blue one here and the red one here. If we gave you the directions, synthesize this from ethyl bromide, hopefully you said the blue choice is better than the red choice. Let's see how to make the blue choice. The blue choice I have now turned into a blue aldehyde and a green Grignard reagent, but both of those things come from a 4-carbon molecule. So if you're needing to synthesize this 4-carbon molecule from ethyl bromide, you're going to need to make a carbon-carbon bond. So here I have shown you how to make a 2-carbon Grignard reagent. But in addition to that, starting with ethyl bromide, adding Naomi, that will do an E2 reaction. We should maybe heat it as well. Kotbu is another good choice. Naomi is the one I typed up. We get this 2-carbon alkene. And then if we add MCPBA, that's a peroxy acid, make an epoxide. So this 2-carbon Grignard attacks this 2-carbon epoxide, protonated in the end, to get this 4-carbon alcohol, butanol, 1-butanol. That 4-carbon alcohol can then be oxidized to turn into my blue aldehyde. Make sure it's a weak oxidizing agent, because otherwise you will get a carboxylic acid, and we don't want none of that. Butanol can be substituted for a BR with PBr and pyridine. HBr could also work. PBr is just what I chose. And then turn that 4-carbon BR into a 4-carbon Grignard. So if we were synthesizing every single carbon in this molecule overall, if we had to show how every single carbon came from ethyl bromide, that's one option of how you do it. Is that the only option? No, but it's the one I came up with. All right, starting on aldehydes and ketones, we need to announce some common names that you should be familiar with. Those top few, we should probably already recognize their names a little bit. Formic acid was a 1-carbon carboxylic acid common name. Formaldehyde is the 1-carbon aldehyde version. Acetic acid was the 2-carbon carboxylic acid common name. Acetaldehyde and propionic acid, propionaldehyde. Continuing on with that pattern, this was butyric acid, it's butyraldehyde, and benzaldehyde is benzoic acid. So those carboxylic acid derivatives are really the root name of all of these aldehyde derivatives too, common names. Here's some ketones that you have to know the common name of. This is a 3-carbon ketone. You can't call it propione ketone. That's acetone. The one in the middle, MEK, that's methyl ethyl ketone. It tells you there's a methyl on one side, an ethyl on the other side of this ketone. Acetophenone and benzophenone, common names you need to know. The IUPAC nomenclature system makes more rules, obviously. The longest continuous chain with the COO is the parent. It ends with -one if you have a ketone, or -al if you have an aldehyde on your parent chain. The COO is given the smallest number possible for a ketone, but it's understood to be carbon 1 of an aldehyde because the aldehyde is always at the end of the chain. If you have a higher priority functional group present, so that you have a different parent chain name, you name an aldehyde or a ketone as an oxo substituent. Let's walk through a couple. This first one has 6 carbons, and there's an aldehyde at both ends. So it's a hexane, but it's a hexanal because there's aldehydes. But there's 2 of them, so it's a hexanediol or hexane diol. That di tells me there's 2 aldehydes. You don't have to give the aldehydes numbers because even when there are 2, they're understood to be at the end of the chain on either side. So then we have substituents here, 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 here. That's 2, 3, 4, 5. And all of those substituents are the same. So it's 2, 3, 4, 5 tetra, because there are 4 of them, hydroxy. 2, 3, 4, 5 tetrahydroxy hexane dial. It's a mouthful. The next one has alcohols, aldehyde, and carboxylic acid. Among those functional groups, the carboxylic acid is the higher priority. So it gets carbon 1, while the aldehyde ends up on carbon 6. So this becomes a hexane because it's 6 carbons. It's a hexanoic acid because the carboxylic acid is high priority. It's a 6-oxo because the aldehyde does not take over the parent name. It's part of the prefix because it's not the highest priority. 2, 3, 4, 5 tetrahydroxy, just the same as the last one. 2, 3, 4, 5 tetrahydroxy 6-oxo hexanoic acid. Ugh, another mouthful. So this bottom left corner has 2 COOs. It has an aldehyde and a ketone, and it also has an alkene. So we have to pick the longest chain that has the most COOs. If I pick this chain, we get both COOs. Carbon number 1 is going to be this aldehyde carbon up here because you give the substituents the lowest number possible. So it's 1 has an aldehyde. Carbon 2, 3, 4, 5, 6 has a ketone. Carbon number 3 has an alkene and an ethyl. So if we put all this together, it's a, sorry, I should have already said it's an 8 carbon chain. So it's an octane, but the highest priority among these is an aldehyde, so it's an octanal. But wait, an alkene is always named in the parent name also, so it's an octene al. The al doesn't have to have a number, but the ene does. So it's a 3-octenal or a oct3-enal. It's a 3-ethyl, and then you have to name the ketone 6-oxo. 3-ethyl, 6-oxo, 3-octenal. One more thing. There's an alkene. Is that alkene E or Z? The highest priorities are on Z-zameside. That's this carbon up here and this carbon up here. Z-zameside. So the full name, Z, 3-ethyl, 6-oxo, 3-octenal. Or you could write it out the way I've typed it here. What's so different about this example and the last one? This longest chain has 2 ketones, not an aldehyde and a ketone. So this 8 carbon chain has to be named as a dione. So it's an octan dione. But wait, there's an alkene, so it's an octene dione. Carbon number 2 and carbon number 6 is where my ketones are. Carbon number 3 is where my alkene is. So you could name it a 3-octene 2,6-dione, 3-octene 2,6-dione, or oct3-ene 2,6-dione, but that's still not the full name. We still have this 3 carbon chain hanging off up here. That's a propyl. It's a 3-propyl 3-octene 2,6-dione. And the final icing on the cake, is it E? Is it Z? This carbon and this carbon are my high priorities. They're on opposite sides, so it's E. You could name this thing E. 3-propyl 3-octene 2,6-dione. Ugh, wasn't that fun? I'm glad it's over. Well, let's start in on a mechanism. Aldehydes and ketones reacting with amines. What kind of amines? primary amines. Let's do it. Starting in on aldehydes and ketones reacting with amines. This amine that I'm reacting with looks kind of fancy. So how do I know that it's the amine that should do the attacking? How do I know that it's the amine that is the nucleophile? Well, these two nitro groups, the nitrogen has a positive charge. He doesn't have any electrons to attack anything. This nitrogen has a lone pair, but that lone pair is pretty distracted by resonance throughout that ring. This lone pair, however, is laser beam focused, ready to attack the carbonyl carbon like that. That's a big thing to draw. This whole reaction takes place in acid, so let us protonate that O- we generated. Well, we want the nitrogen to stay, but we do want the oxygen to go away, but we need to clean up some base, take a hydrogen from that nitrogen, clean up that nitrogen to make that nitrogen neutral, and then I get somewhere significant. What is this significant place? This is my neutral tetrahedral intermediate. This neutral tetrahedral intermediate is ready to protonate a leaving group and let it go, let it go. So protonate the O. Why do I know I'm protonating the O? Because the O started out connected to my thing, my reactant, and I want it to go away. I want my nitrogen to stay because it's a new addition. So I get here, and then I fold it down, kick it out. Almost finished, but not quite there yet, because at this point, my nitrogen is still positively charged. I need some base in solution to come clean up, some base somewhere. Ta-da! This thing. What the heck is this thing? This functional group, C double bond O, is an imine, an imine, This specific one, because it's got an N double bond N, is a hydrazone. That's not really a super important thing that you know, because we're missing the lab that relates to. So this is a pretty big mechanism. Maybe I'm just a large drawer, but it's a pretty big mechanism, but it's not very complicated. It's attack. Protonate, deprotonate, protonate, deprotonate. Exchange protons as many times as necessary to end up with a nitrogen doubly bonded to carbon. Only 2 steps in this reaction are not a proton transfer. That's the first one. Attack the carbonyl carbon. Proton transfer. Proton transfer. Proton transfer. Fold down, kick out. Proton transfer. Product. So this is not a complicated mechanism. It's just put the H's where the H's need to go in order to make a good leaving group and let it leave. Your leaving group needs to be positively charged in order to leave, because your reaction is taking place in acid. So if you're paying close attention, you might say, well, if it's taking place in acid, why didn't you protonate this carbonyl in the beginning before you attacked it? that could have made you save a step here, protonate first and get to here. Well, I'm being consistent with your textbook that you attack the carbonyl first, then protonate, deprotonate, reprotonate, fold down, kick out. I'm being consistent. So why do we not protonate if this thing is ran in acid? The truth, this acid has to be a very small concentration. A lot of times it will say a trace of acid. Why is that so important that a trace of acid be used? Because we're reacting an aldehyde and ketone with an amine. And the first thing that you knew about amines way a long time ago was that amines are good bases. So if you have a lot of acid in solution, are you going to have an amine? No. If you have a lot of acid in solution, you're going to end up with an ammonium. And if you have an ammonium, can you attack the carbonyl carbon? I think not, because this is no longer a nucleophile. So the amount of acid is very important in a reaction like this. And the pH of a reaction is very controlled in a reaction like this. If it's too acidic, you don't have a nucleophile. If it's too basic, you won't ever get your leaving group to leave. So there's a whole section in your textbook that talks about controlling the pH of a reaction like this. Maybe you should check it out. Before we move on to the next thing, there's something I want to point out. I have been lazy. This reaction said equilibrium arrows, and I neglected drawing them for the remainder of my steps, but I should have drawn them. Why does it matter that we draw equilibrium arrows? The truth, I don't get obsessed about equilibrium arrows, but this is all equilibrium processes. What did I say most of these steps were? Proton transfer. That proton, the protons in solution, can be exchanged between a lot of different things in that solution. And so all of these steps are reversible. How do you control equilibrium favoring one thing over another? Well, obviously, it's all about Le Chatelier's principle. I'm going to draw just a simple amine here, not because it matters, but a simple amine so that we can see more easily how Le Chatelier's principle works in an example like this. If I have an aldehyde or ketone plus a primary amine with a trace, a little bitty baby bit of acid, I get an imine and water as the side product. Where did that water come from? It got folded down and kicked out right there. So water is my side product. If you're taking advantage of Le Chatelier's principle to control equilibrium here, if you add a lot of water and a little baby bit of acid to an imine, that's going to favor the reactants the way I have this written. The reverse reaction, when you add lots of water to an imine with a little baby bit of acid, you get a hydrolysis reaction. The reverse reaction is hydrolysis, chopping an amine with water, an imine with water. If you add lots of amine, A-M-I-N-E, lots of amine to your aldehyde or ketone, you can get it to favor imine product, imine formation. You remove water, you're going to favor making more imine stuff. So we have just drawn the imine formation mechanism. Note, you are also responsible for imine hydrolysis mechanism. We're not going to draw it together, but you're responsible for it. Do you think it involves a lot of proton transfers? Uh-huh. Do you think it follows the principle of microscopic reversibility and goes through every single one of these intermediates, but only in reverse order? Uh-huh. That's why we don't have to draw it together, because you learn it forward, you can also do it backwards. I believe in you. So that's a primary amine. We got a hydrazone product. The reason it was a hydrazone is because our ketone reacted to form an N single bond N imine, amine. The comment down there about structure determination, that's related to the lab that we're missing. Sorry, boo-hoo. Here are some other amines that are primary that could be used to convert aldehyde or ketone into an imine. If I have hydroxylamine, who's more nucleophilic, better at attacking, better at giving? Who's a better giver, nitrogen or oxygen? Nitrogen, so you bet it would be the nitrogen that would attack. In hydrazine, well, either one of these nitrogens would attack. In phenylhydrazine, this nitrogen has a lone pair that's distracted, while this nitrogen has a lone pair that's laser beam focused, so it would be that nitrogen that attacked. And in semicarbazide, same story. This one laser beam focused. The other two nitrogens are distracted by resonance with that COO carbonyl thing. So be aware that when you're presented with different looking compounds, amines included, pick out the one that's the best nucleophile, and that is where you attack the carbonyl carbon. Ready to draw a Wolff-Kishner reduction reaction? It'll be fun. Let's do it. Wolff-Kishner. Do you remember what Wolff-Kishner does? I hope so, because that's kind of essential in knowing how the heck to draw the mechanism for it, right? Yeah. Wolff-Kishner is hydrazine. Hydrazine and hydroxide and heat. We just saw that nitrogens, amines, attack carbonyl carbons like that. O minus NH plus. We're going to do something right here that some people think are illegal, but I think I trust you enough now to allow you to do it. I'm going to do an intramolecular proton transfer. Is that likely how it happens? Nah, but that's okay. What would really happen, we think, is the oxygen would get a hydrogen from something, and then the nitrogen would lose a hydrogen, like maybe hydroxide comes to get it. But we end up here with a neutral tetrahedral intermediate. Man, my spelling is really great today. A neutral tetrahedral intermediate. So I'm ready to fold down and kick out my hydroxide. What? Hydroxide is a terrible, horrible, no good, very bad leaving group. Why do you fold down and kick out hydroxide? Well, this whole reaction is ran in hydroxide. So there's already a lot of hydroxide around. So it's okay. Fold it down, kick it out. Hydroxide. You kicked it out. That hydroxide can deprotonate to get you here. Ta-da! This is an imine, an imine. And some of you that aren't sleeping while you're watching this say, but wait, Wolff-Kishner doesn't make an imine, an imine. Wolff-Kishner totally gets rid of the COO. Wolff-Kishner totally gets rid of the carbonyl. This is the product that Wolff-Kishner is supposed to make. That's right. This COO is replaced with two hydrogens. Well, the Wolff-Kishner reduction goes through an imine. This imine then goes through extra steps. We're going to switch colors here to say the first bit of that reaction is simple imine formation. But what comes next is unique to the Wolff-Kishner reaction. The Wolff-Kishner is a reduction. it gets rid of a COO. And the way it does that is you must react with hydrazine because the H's on this nitrogen are quite important. You can deprotonate that one of the H's on that terminal nitrogen after your imine is formed to get here. This has a resonance form that looks like this. In on carbon, no, minus on nitrogen versus minus on carbon, this is the more favorable structure, but this one is going to get me where I want to go. So I can deprotonate maybe water that's around in solution from hydroxide reacting with some H's to get here. Oops, can't believe I did that. Well, let's try again because I have no whiteout and I'm not going to edit this out because I don't want to. I get here for real this time. Really have the carbons that belong. Don't know what I was thinking. This hydrogen here came from the water or some other weak acid in solution. This is still not what I want, but it's closer. So how about hydroxide come to take another H off of that terminal nitrogen? Do it. Nitrogen with a minus, that's reasonable. But nitrogen with a triple bond is more reasonable. Let that nitrogen go as into nitrogen gas. This is not resonance here. We broke a sigma bond in that reaction, not resonance. Then that benzylic anion can get protonated just like the last one did with maybe some water in solution where hydroxide reacted with some acid. So it's a pretty lengthy mechanism, but we turned our carbonyl ketone into two H's. That's the Wolff-Kishner. Why do we draw the Wolff-Kishner mechanism now? Because the Wolff-Kishner mechanism goes through an imine, and now we are responsible for how the imine is formed in general for other reaction types. But we're also responsible for this whole giant Wolff-Kishner mechanism. You're welcome. That was the Wolff-Kishner. It made ethylbenzene in the end. Wolff-Kishner has a primary amine. What if I started with a secondary amine? We're going to do this one too. Primary amines react with aldehydes and ketones to make imines, imines. Secondary amines can also react with aldehydes and ketones in a very similar mechanism, but there's a little bit of difference at the end. But the beginning is all the same. Attack the carbonyl carbon. Protonate the oxygen minus you just made. Almost forgot my hydrogen. Some base in solution. Deprotonate the nitrogen. And here we are, a neutral tetrahedral intermediate. I started out with oxygen connected. I want to keep nitrogen connected. So I need to protonate my leaving group before he leaves. My leaving group is O. Protonate my leaving group before he leaves. O. And then hopefully you can guess it. What comes next is one of the two non-proton transfer steps. Fold down and kick out my leaving group. And I get here. Here. Dang it, I'm half asleep. My nitrogen's in the wrong spot. I get here. You would think I'd be more professional than this, but no, I'm not. We know me. You get here. This looks like an imine, an imine, but it's a nitrogen with a positive. It's an iminium. This iminium ion is not the final predicted product because we want a neutral product in the end. There's no hydrogen on this nitrogen to make it neutral, so we're going to need to give electrons to that nitrogen some other way. So if I consider this resonance structure, where nitrogen got his lone pair back, that's a single bond, nitrogen got his lone pair back, there's a positive down here. So this structure that's black is better than this structure that's pink. Why? So how do I make a final product where everything is neutral? Some base eliminates a hydrogen from a neighboring carbon to give me my final product. Eliminate a hydrogen from a neighboring carbon, and you get this. This compound has an amine, A-M-I-N-E, and an alkene. So this one, it's not your friend, it's your enamine. I hope you like that one. This is an enamine because it has an alkene and an amine in the same molecule. The mechanism of enamine formation is almost identical. In fact, it is identical to the imine formation until you get here. This iminium ion, when you were making an imine, you still had a hydrogen on here. You lose the hydrogen, you're done. There's no hydrogen directly on the nitrogen to lose, so you have to lose a hydrogen from a carbon. Which carbon? The carbon that's next door to your carbonyl in the beginning. If you kind of picture this back to when we talked about E1 kind of eliminations, this carbocation is your alpha. Next door to alpha is beta. So you're really losing a beta hydrogen to make your final ene in your enamine. When you're making an enamine that is not symmetric, does not have symmetric beta hydrogens here, you're going to follow Zaitsev and make the most substituted alkene by eliminating the hydrogen from the beta with the fewest hydrogens. If you need me to repeat it, just rewind. Two more small points to make about this enamine formation. Like the last one, this one started out writing it as equilibrium, and then I stopped. Well, actually, I did do it right there. Go me, hooray. This is an equilibrium process. This whole reaction, just like the last one, is an equilibrium process. All of the steps are totally reversible. There are proton transfers, proton transfers, proton transfers. In fact, just like imine formation, there are 2 steps that do not involve a proton transfer. So you have to be comfortable with proton transfers. And the one other thing is, do you suspect this is a lot of acid? No, because if you had a lot of acid, your amine, A-M-I-N-E, would not be able to attack the carbonyl. It would get protonated and no longer be a nucleophile. So that same advice about imine formation being run at a certain pH range, same dang thing here. This is a secondary amine forming an enamine. We made an enamine. That enamine. Do you suppose you know how to control equilibrium here? I hope so. One more thing about a lab we're going to miss. Let's draw this one and talk about it on paper. So we're not going to draw a whole mechanism for this one, but we're going to talk some details about it anyway. If I put together, combine a ketone and a primary amine, I end up making an imine, an imine, when those 2 things are in solution together. Well, that's not different from what we've done, but this slide says this is called reductive amination. A reductive amination is specifically when a ketone or aldehyde and an amine get together to make an imine, an imine. An imine is definitely an intermediate in your reaction here, in your reductive amination, but you're also adding sodium cyanoborohydride to this mixture, and sodium cyanoborohydride can reduce your imine like that to make it an N minus. And we don't have to, but we'll highlight the hydride that got donated in blue. And we don't say the solvent on the slide. I wish we would have, but let's say the solvent in this reaction is ethanol. So ethanol is there to protonate your nitrogen, make sure you have a neutral compound in the end, a neutral amine, A-M-I-N-E, neutral amine. The reductive amination starts out with a ketone or aldehyde and a primary amine, goes through and makes an imine, an imine, and that imine gets reduced to finally make you an amine, A-M-I-N-E product. Reductive amination. I usually talk quite a bit longer about this reaction than I'm going to right now because we do a lab with it. But since we're missing that, I'm going to shortcut what I'm going to say a little bit, not because it's something unimportant, but it's something that really pertains to lab. One thing I will take the time to say, what's easier to reduce, an imine or a ketone? An imine is slightly easier to reduce, so that's why you can add the reagents together like this. If you had all of this all stirring around in a pot all together, you would get the product that we just predicted. However, if you have all of this stirring around in a pot all together, you will not get the product we just predicted. Wait, what? What's the big difference? Sodium borohydride versus sodium cyanoborohydride. This one is a weaker hydride donor than that one. So what happened was, this hydride donor is capable of reducing your ketone. So if you add all of this in solution together, sodium borohydride will reduce your ketone to an alcohol, and an alcohol plus an amine does not make an imine. It will not yield the primary it will not yield the amine product you were aiming at up here. You get an alcohol and an amine that are unreactive with each other because sodium borohydride is so good at reducing ketones that it cannot wait around for the imine to form. Sodium cyanoborohydride is a much weaker hydride donor, so sodium cyanoborohydride does not reduce ketones. So these guys react together first to make an imine, and as the imine is formed, sodium cyanoborohydride starts to reduce it. So the order of addition is quite important in reactions like this. This can all go together. This has to be number one, let those guys react to form the imine. This must come later, after you've given the imine a chance to form. Hopefully that's understandable. If not, oh well. See you next time.